Hello and welcome. In this video, we're going to take a look at top-down design. It's another one of these abstract concepts in software development that I'm hoping to help you make some sense out of by some simple examples. Now, this video assumes that you have gotten some basic programming experience, whether it's with MATLAB, C, Java, JavaScript, Python, or any other programming languages. And I will be using a little bit of C for this particular video. However, that is not going to be the primary focus. The goal of this video is that you get some familiarity with what top-down design is, and particularly what are good programming or good development practices. So to begin with, let's get started by talking a little bit about why we need top-down design. And I guess I can start off by talking about what it isn't, or rather what you've been doing prior to dealing with top-down design. And so in the past, if you think about it, you were challenged with a problem or project and maybe use a scripting environment like MATLAB or Python, and you simply put all of your code inside the function that runs when you run the scripting environment. In MATLAB, it would be the main script, and you ended up with a script that might be 500 lines long or some length that started to make it kind of hard to use. Maybe you ended up having to copy and paste code multiple times because you were essentially doing the same process over and over again, etc. And the idea is that we can now employ a better approach to designing software. In other words, a more systematic approach. Again, much like one of our earlier videos where we're talking about the software design process, this is another process that you want to follow. It's sort of a set of recommendations that you want to follow in creating good software. So what's the benefit to breaking down your code into more functional or modular units? Well, there's a couple, not the least of which is the fact that it's easier for you to handle. In other words, you're not scrolling through 500 lines of code looking for a bug. You can also break it into multiple files. Again, easier to manage, easier to name. And the idea is that if you saw a block of code that you might be using over and over again, you would simply pull it out of that main body of code, push it over to a separate file, and it would ultimately make your main file, or that first file, ideally smaller and easier to read. And you would simply then make calls to that secondary file. So it's basically allows for you to have a better structure of your code, of your project, of your solution. Now, what do we get from that? Well, when it comes to isolating these algorithms or these processes, it's easier to test. And so for debugging purposes, you can then isolate that function that you pulled the code out, put it into a separate function, into a separate file. You can then isolate that for testing purposes. Perhaps you're in a scenario where you are dealing with a customer or a client that has not yet given you all of the requirements for your project, but you know, for instance, that you might need a sorting algorithm or a search algorithm. And so you can test that sorting or search algorithm separate with perhaps some test data that you have even before the client or the customer gets back in touch with you with some real valid data, or maybe even some changes in the requirements. The other thing that it also allows for you to do is to reuse that algorithm or that process, not only in a single project, but also across projects. And we'll see the method by which you do that differs depending on which language you are working with. And sometimes you can actually make a separate standalone library with just a collection then of these algorithms or these processes that can then be leveraged in multiple different projects. But for right now, we want to think of the concept of being able to pull out an algorithm that you've perhaps copied and pasted multiple times in a main or in one script, pull it out, put it in a separate file, in a separate function, and then just simply call it from there. Now, what are some of the advantages? It just simply makes your code easier to repair. In other words, if there's a bug, same with maintenance, and also ultimately makes the whole process more sustainable. In other words, ideally, it's part of the software development process that will lead to more sustainable code that can be used longer and longer. And naturally, then an extension of that is, or another feature of that is the ability to extend your code. And what that essentially means is that you can use your code for uses beyond the initial project. In other words, maybe you can use that search or that sorting algorithm in ways that you did not anticipate using it when you were trying to solve that first problem. Now, before we go any further and before I go into some visual examples for this, I want to talk a little bit about why you sometimes don't want to do this top-down design. A great example of that is just simply when you're prototyping something. In other words, if you're just trying to put something together real quick for someone or maybe for yourself to test a proof of concept, then it's probably not going to be necessary for you to go through and create this top-down design or approach that you would ultimately use for a more sophisticated project. And you'll find that there's kind of a balance in that if the project itself lends itself to more of a structured approach, then definitely want to employ this top-down design that we're going to see in just a little bit. But if you're just trying to solve something quickly, figure out if this particular sorting algorithm or the search algorithm will work for you, then it's probably okay to simply go ahead and write it in a single script and don't focus so much about the structure, simple script or a single function or so on. So continuing on with that, let's look at some examples in C. Again, these examples are going to be pretty similar in most other programming languages as well, but we're going to stick with our C command line executable. If you've worked a little bit with C, you should recognize that that is the main entry point or main that accepts the argc or argument count. In other words, the number of arguments that are passed on the command line, followed by the argv, which is essentially those arguments that are passed on the command line. And you should probably also recognize this is essentially a visual representation of one of our earlier projects where the main just simply went ahead and called the function A. And you can see here that if you just follow this path here, you'll see that main calls function A, and function A then simply just returns control back to main when it is done. In other words, there's no real way to get any information into function A, and there's no real way to get information out of function A. Essentially, what it's doing is it's simply displaying perhaps a table, or maybe all of the input and output is contained within the function. And so there's really no way to know whether that function was successful. There's no real way to parameterize the values that are passed to it, etc. It's essentially a very crude function where you can simply just use it to test something. And there will be scenarios where you will want to do that. Everything in it is self-contained. Likewise, function B does the same, and so we're calling it following the successful return from function A, and then function B finishes, returns back to main, and then function C is called, and then ultimately returns back to main. Effectively, what we've done is we've simply just encapsulated some process inside of function A, inside of function B, and inside of function C that may not have any real relation with each other. In other words, A doesn't depend on B, B doesn't depend on C, and so on. So probably the simplest example of top-down design that you could imagine is simply encapsulating a process. So let's take this a step further now. In function A and in function B, there happens to be an algorithm that is very similar. Notice that function A and function B, as well as function C, doesn't accept any input arguments and doesn't return any output arguments. And we'll talk about that in just a second. We'll actually improve on this. And then function C has some other algorithm that may or may not be somewhat related to the algorithm that's in A and B, but A and B share an algorithm. In other words, basically what you ended up doing is you simply ended up copying and pasting code from function A into function B. No changes. It just so happens that they use the same algorithm. And that's not very efficient, because if you made a mistake in the algorithm in function A, well, you'd have to go track down those changes in function B. And so the same process here, function A is called, it runs algorithm A, but then ultimately it returns back to main. Likewise, B is called, returns control back to main, and C is called, and it ultimately returns control back to main. And again, we can talk about why this is not a great approach. As a matter of fact, we will when we start looking at different control structures in our C programming language. But for right now, basically A is called, B is called, and then C is called. Those functions are called. All right, so taking this a step further, I have now pulled out the algorithm that was in function A and function B. You can go back a slide see what I'm referring to. And you can see here that basically what I've done now is I've created this new function called function D that effectively was the algorithm that was found in A and B, and they no longer reside in A and B, but are essentially just called from function A and function B. Now notice I still don't have anything listed as far as any of the input and output arguments. We're going to improve on that in just a second. It would be kind of a little hard to pull this off. There would only be a few scenarios where you would not be passing any arguments to function D from function A, but likewise function D then simply returns back to function A. Function A then returns back to main. Function B is then called. Function B calls function D. And likewise, function D returns back to function B and back to main. Then finally, over here, we have our function C that I went ahead and abstracted that second separate algorithm out from. That would not necessarily be done. It just depends on whether you predict that that algorithm B could be useful in the future. I went ahead and did it just to demonstrate that it can be done. You may consider simply leaving that algorithm B inside of function C. And again, though, there's no input and output arguments being passed between any of these functions. And likewise, as before, function A is called, then function B is called, and then function C is called with no control structures or anything like that. All right, so let's take this a step further and let's start to investigate how we would practically do this with passing information between those functions. And we're going to start off by going all the way back to that first example where we had, again, this very simple top-down design where our main does multiple things, essentially one right after the other, in that our main calls our function A. It doesn't accept any input arguments, and we know that because there is this void listed as an input argument. Basically, it says it's a way of saying that it does not accept any input arguments. It doesn't need any information to run. And likewise, it returns nothing. That's the return void here. In other words, basically, it accepts no input arguments and it returns no output arguments. So you have very little way of knowing even if function A was successful. You would do this only in certain scenarios. Perhaps you might be writing a help function where you don't really care if the help function accepts any arguments because you're not going to have specific help, you're not going to have contextual help, and you don't really care whether or not the help function was successful in running. Basically, it either displayed the command line or something else happened catastrophically that you didn't really have any control over. In this case, you would basically accept a void as an input argument, or rather accept no arguments, whichever way you want to think of it. And you would also return no output arguments. Now, our second function B improves on this just slightly, in that it accepts an integer. In other words, basically, we pass an integer x to our function B. It does something inside of it. Maybe it prints out a table, but it has no way of communicating back to main. The return of the control from B back to main still occurs, but there is no information that is being passed from B back to main. Again, basically, main has no way of knowing whether or not function B was successful in whatever operation that you ask for it to do. Again, there are scenarios where you may run into this, but they might be a little bit limited. Now, the third scenario, which is more common, and there are a couple of those we could look at later on, is that you would pass an argument to a function. In this case, we're going to pass our int x again to function C, and we are going to also accept a return value back to main. So in other words, when this function is done running, it returns control back to main, but it also returns a value, in this case, an integer that main can then use. And the simplest example I can give for you on function C is that you pass an integer x, you add 1 to that integer, and you simply return whatever that value is. So in other words, if I pass 5 to function C, I would simply get 6 as the return value on this return path. And again, because we're not assuming any control structures inside of our main, we are simply looking at the structure and how these functions relate to each other. You can see then how main would call each of these individual functions. All right, so now let's combine the two concepts where we leveraged that algorithm in our function A and B, and we combined it into a separate function D. I've also thrown in a new data type of double. So we now have void, int, and double. And you can see here that we also have our function E that is hanging out down here. And I've added some input and output arguments to all of these functions. Now, again, our main just simply calls our function A. It passes an int X. It will ultimately return an int back to main, but first it makes a call from function A to function D. And you can see here that it's passing a double, and then it returns an int. And a great example of this might be where you have a round function or a floor function or a ceiling function where it takes a double and it returns whatever the integer would be as a result of either rounding, flooring, or applying the ceiling to a double value and returning an integer. Again, these would probably be very specific reasons for doing it this way, but the principle still stays that you have combined now that functionality that was previously in A and B into a single function that can be then called from other functions. Function D then returns control back to function A, passing an int, and then ultimately whatever else is done inside of function A, another int is returned to main. Likewise, we can do the same thing now with function B. You'll notice that it also accepts an int y as well as returning an int, and it passes a double to our function D and then returns back an int from function D to our function B, and then ultimately that int or some other process occurs and then an int is returned back to main. Now, for a little bit of variety here, let's take a look at our function C. Again, our function C accepts an int. In this case, we're calling it int Z, and nothing is being passed to our function E. You can see here that I have no input arguments, but it does, in fact, return an integer when it is done running. And a great example of that is a function that might be used to get the current time. And again, we won't talk about date time formats right now, but basically what it does is it returns, for instance, the integer count of the number of minutes or number of seconds, or perhaps the number of ticks since an epoch, back to our function C. Function C does something with it, and you'll notice now, interestingly enough, our function C has no return value, and so maybe this particular function assigns a file name to a file on the file system with a date timestamp. And again, that's a specific scenario, but I can see scenarios where you would do something like this. The point is that you can now see how we have this hierarchical structure. We could have written all of this inside of main. Main would have gotten incredibly long and very hard to support. But now what we have is, instead of a single function that had all of our code in it, we actually end up with 1, 2, 3, 4, 5, 6 functions. And some of the functionality is actually reused between two of our other functions. And I think as you imagine, as our project gets more sophisticated, more complicated, more complex, that you could see some real advantages in this approach. So hopefully you found this video useful. If you have any questions, comments, or concerns, don't hesitate to reach out to me. And thank you for watching.